Thank you for organizing this and thank you for inviting. The title is a bit different. Now we have almost for about a year, magnetars as the sources of fast radio bursts. They are no longer candidates, but I will give you some touch of both phenomena, which are extremely interesting, and eventually they merged together. First, magnetars, which is my long-term field of interest, that have started with the event whose light curve is shown below, back in 1979, more than 42 years ago. It's an event called March 5th event, which was detected with some gamma ray instruments of that time. At that time, there were only Soviets and Americans in space. So they were monitoring each other, and one of Russian satellite caught this very extraordinary event. It was very bright. Notice the peak intensity in the scale goes about 50,000 counts per quarter of a second. And soon after, within a second or so, it goes down to about 2,000 counts per a quarter of a second, but it oscillates with a very precise period of about 8 seconds. This was observed in gamma rays, and at that time, gamma ray bursts were all intriguing, and they were for a long time a common understanding that gamma ray bursts are caused by neutron stars, because this is showing the pulses of a neutron star. You cannot have a black hole which wouldn't pulse. You cannot have a white dwarf which is not able to rotate at this rate. And about 20 years after this event, there was this idea put forward by two theorists, Duncan and Thomson, who suggested that neutron stars, powered by their extra strong magnetic fields, stronger than typical neutron star magnetic field, which is on the strong side, around 10 to 13 Gauss. These objects, termed magnetars, might even be even stronger in magnetic field strength, so that with the budget of this magnetic field, they can make bursts as seen in March 5th event. There were some critical arguments against it, such as the luminosity is so bright that the radiation of this intensity could simply break apart the neutron star. Incidentally, in the same year, another theorist, Bohdan Paczynski, showed that in the case of highly magnetized environments, the Eddington limit, which is obtained for non-magnetic Thomson scattering cross-sections, can be suppressed so that the luminosities above the Eddington limit can be perfectly fine. So these two important suggestions, supporting quite well each other, brought up this idea as early as 92. And then over the time, bursts of typical intensities were observed. In this plot, I show you a typical burst. Typical meaning short in duration. Look at the time scale. It lasts, the whole thing lasts about 0.1 second and seen mostly below 100 kiloelectron volts. Even during this short time interval, luminosities are in the super Eddington limit for non-magnetic derivation, of course. And typical bursts usually don't show any emission following the main event. They are just the main events. But when they come, sometimes they come in so many, one after another. As you see in this case, a magnetar in its most active episode seen with XMM Newton, in about 50 kiloseconds, there are more than 400 bursts. So they occur quite frequently, one after another. But these are typical short events. There are some more energetic events which last longer. In this case, a couple of seconds or tens of seconds. And some of these do show the individual pulses of the underlying neutron star. In this case, 5.2 seconds. And sometimes you don't see it in gamma rays, but you see brightening in X-rays following these what's called intermediate events. In the case of intermediate events, luminosities are even higher. They reach the level of 10 to 42 ergs per second. There are quite some examples of intermediate flare. This is another magnetar, and yet another magnetar showing a very strong burst, intermediate flare, with a tail extending thousands of seconds. We don't know where it went because this is the point where the observation stopped. So even at the end of this observing run, it was above the pre-burst level. And you see on the tail, tens of short bursts that occurred. And this is another one. This is SGR 1900 plus 14 that shows really interesting bursts. They look like intermediate flares and short events, all within about 30 seconds. And at the highest energy end, there are the giant flares. The first one you see on left top is already what we have seen in the first slide. This is from a magnetar in the Large Magellanic Cloud, which is about 50 kiloparsecs away. So we only could see, of course, with the technologies of 70s, only about 6 or 7 periodic cycles. With the technologies of 90s, this burst was observed. This is SGR 1900 plus 14. It's in our galaxy. It's at a distance of about 10 kiloparsecs. And this burst occurred in 27 August of 98, started with really bright initial hard spike, spectrally hard, and then within seconds decayed considerably, almost 2 orders of magnitude, at which we started observing oscillations at the spin frequency of the underlying neutron star. That's about 5.2 seconds. About 6 years after, 6.5 to be more accurate, in December of 2004, another galactic magnetar, SGR 1806-20, exhibited almost the same type of burst. Here, X scale is linear, so it may be a bit different in scaling, but the initial very bright rise here is spectrally hard and then comes down significantly, almost 2 orders of magnitude, at which you start seeing the oscillations, in this case, at the spin period of 7.48 seconds. That's the spin frequency of this magnetar. According to the magnetar theory, which was put forward in 92, but later on developed to explain many aspects, one important aspect, of course, is the mechanism behind the bursts, which is introduced quite extensively in their 95 paper, and still it's one of the most comprehensive prescription of magnetar burst making. Well, here we have the case of magnetic field lines frozen into the crust of the neutron star. Extremely strong magnetic fields possess extremely large magnetic stresses on the crust. And this stress, going as the square of the magnetic field strength, generates instabilities. And these instabilities shear, twist magnetic fields, which then lead to the acceleration of charged particles, generating fireballs trapped in the magnetic zone. Very quickly, the instability to occur when the magnetic field stress put on the crust, what you see on the left-hand side, the magnetic stress would simply bring the crust to a critical level, which are quite well understood by now. And it breaks at one point. And you can see with this simple argument that if you have a magnetic field either in the dipole or multipolar components exceeding some level, 5, 10 to 14 in this case, if you take the shear modulus to be 10 to 31 ergs per cubic centimeter, and the strain to be 10 to minus 3, this is how much magnetic field strength you would need. For magnetars, this is easy. And of course, a weaker magnetic field can also do similar effect if the combination of shear modulus and the strain are lower. Therefore, in this mechanism, you can get bursts. But bursts that you see are not directly the crustal dynamics. There are some in-between steps. The crustal disturbance would lead to the formation of a fireball, would then cool, radiate, and that's what we observe as bursts. But there is another possible way of making magnetar bursts. That is via magnetic reconnection. In the case of magnetic reconnection, again, strong magnetic field lines, either closed field lines or relaxed, they can break, split, and reconnect, but at a slightly lower energy level. In this case, the energy difference between the initial and final state would come out as the radiated energy. We are very familiar with this process. We know that our sun does this. We observe solar flares. We even experience this process in our neighborhood, especially in the magnetopaws on the side that's not facing the sun. Occurs from time to time, split and reconnection that would be observed as excess emission in the aurora lights. In the case of magnetar magnetic fields, the similar process might take place as described by Thomson and Duncan, later elaborated by Lutikoff in 2003. And this is another possible way to observe the energetic bursts that are very short in duration. Let me tell how many magnetars we are talking about. Not as many as you would think. There are about 3,000 neutron stars known in our galaxy, and the number of magnetars is about 30. But this number is a lower end, which I will explain why. The earliest known magnetars are the source of the first giant flare in the Large Magellanic Cloud. And these two were already known since 1979. They were emitting short bursts. Eventually, in 98, another burst source was discovered. This is typical bursting magnetar. And in the same year, this 1900 made the first galactic explosion of a giant flare. And in 2002, another group of related objects were shown to emit bursts. So a magnetar family with bursting capabilities extended to about a number of 10. And in 2002, the first transient magnetar was discovered. Up until 2002, these point X-ray sources emitting bursts from time to time, they were persistently emitting X-ray sources. But in 2002, we became aware of transient magnetars, which are dim, below X-ray emission, below our detection capabilities. But now we know that there is another group which might outnumber the known magnetars because they are below our detection limit. So with transient magnetars, this number started increasing, and this guy, which I will refer in the rest of my talk quite often, emitted the giant flare in 2004. And then Fermi, GBM, Swift, Bott started populating the magnetar family, and now we have about 30. In 2014, we have added another source to this list, which is this guy, 1935. Again, a source that will be in the focus of this today's talk as well. So altogether, these are a bit less, but the number of 30 magnetars in our galaxy. I presented this slide first in China. That's why I made it red and yellow. Now I like it because it's also the colors of my favorite team. Beautiful. Anyhow, Let's look at this giant flare of 1806. It's so amazing, and it looks very similar to what was seen from 1900 plus 14 in kiloparsecs away. It's like a carbon copy. So nature does the same thing if it has the same conditions and it has the same ingredients. Perfect example of scientific method. Here we see the giant flare onset, very hard, and then oscillating tail. It lasts about 6 minutes, 5 minutes. And you can see with your naked eye, the variations, fluctuations, changes in its pulse profile, which is showing the magnetic topology on its surface. It's simpler here and then starts becoming more complex just about a minute later. There you go to see the changes easily. Within a minute, it gets this component stronger. Another 2 minutes, it changes even further. And a couple of minutes later, another component that starts taking to become dominant. So giant flares are remarkable. And this giant flare occurred in 2004, was followed at different wavebands. What you are seeing here is about 50 kiloelectron volts using Swift bot, hard X-ray, soft gamma rays. In radio, this giant flare showed a very long-lasting expanding nebula. This is about 2 weeks, not even 2 weeks, about 10 days after the event. You see before the giant flare, there is nothing in this region as seen with VLA, one of the most powerful radio interferometer. And in 2 weeks after the giant flare, you see this very bright emission. And it decays quite rapidly. On this scale, you see its decay in many radio bands over the next couple of weeks. After this initial study, of course, this emission was followed with the same instrument and some other radio, and they saw that it's actually re-brightened. We are talking about the radio blob. And it was still bright year after this, which you don't see, but they have the data. Here they presented only about 2 months after the giant flare. Interestingly, this radio observation was polarized in this portion especially, where the intensities are still quite high, but not the highest, because it wasn't done in that mode. And the polarization is not seen about after this re-brightening epoch. So I'm not going to talk about everything because I want to come to the main connection here. I want to come to the connection with fast radio bursts. If you want to learn more about this radio polarization, linear polarization, please refer to these 2 papers. And this radio blob is expanding. As you see here, in milliarc seconds, it's significantly expanding in days, from about 60 milliarc second diameter to almost 300. So all these things, following the giant flare, the emission of radio blob, very long lasting, highly energetic, polarized, were in our pockets. In 2001, someone very colorful in our field, Duncan Lorimer, and his wife, they are really amazing. They brought so many new things in our life. He was performing an observing run at the Parkes telescope, 64-meter telescope, and they observed some strange type of rapid variations in X-ray radio flux. Back in 2001, they didn't know what this was, but one thing that was really amazing, this short event lasting less than 5 milliseconds was extremely bright, and it was showing extremely high dispersion measure, the interaction of radio waves with the interstellar matter. So if it's a high dispersion measure, you say that it must have been interacting with matter for a long distance, meaning that it must be extragalactic. It took many years for them to really digest this and finally make a very impactful paper in 2007, which became the start of this new interesting field. It was not the first one. With Parkes, actually, even before 2001 July, they observed in January and June another ones, but they chose to publish the strongest one. But now this is the sample that they have actually collected before they reported this new phenomenon. So they are short, they are bright in radio, and of course, with something this bright, many other telescopes could observe others. And over the next 10 years or so, the field of FRBs went from doubtful to something extremely interesting. In 2016, up until 2016, in about 10 years, there were so many theories suggested, which were literally trashed with the discovery of the repeater. Some FRBs come from the same region. So they cannot be just a catastrophic event like a supernova explosion. Maybe some, but not all. And those repeaters, some of them, and some FRBs were localized to some distant galaxies. So they are really coming from extragalactic distances. Here is a very nice chart of radio sources, the differential measures of the radio sources normalized by the differential maximum differential measure of the galaxy. So anything you see above are expected to be extragalactic. Anything below are expected to be within our galaxy. And as you see, FRBs in blue stars, SMC and LMC pulsars you see in red diamonds are extragalactic, no exception. All radio pulsars and rapid radio transients are galactic. Now, these are really extreme objects, extreme bursts. Let me tell you very quickly what makes them extreme. We define the brightness temperature according to the radio end of a Planck curve, Rayleigh-Jeans limit, which would give you, with the intensity at given frequency, a brightness temperature of 10 to 35 Kelvin. This is incredibly high. And we observe this from such a long distances. So there must be a coherent mechanism that's operating in these engines. By now, we have seen that many FRBs are polarized. And with the installations specific to FRBs or general radio bands, we have now a lot more capabilities of observing these energetic events. In 2019, I attended this conference in Amsterdam where people were talking mostly about magnetars, making FRBs. They were, of course, using the knowledge of radio pulsar emission mechanisms, but scaling up to the field strengths of magnetars, either via curvature mechanism or some Maser mechanisms. But it seemed at the time that they were so motivated by the emission of giant flare igniting the bright, long-lasting radio blob. That was very interesting. And at that time, of course, the connection would only be put together if a galactic magnetar would emit an FRB. And that didn't last very long. We didn't need to wait for a long time. So I call this very nice surprise of the pandemic. Up until then, and now, there are about 150 FRBs reported. This number will be about 600 very soon when the first catalog of CHIME, the Canadian hydrogen map, is released. They have compiled the first year's observations. It has nearly 500 FRBs, and it is full of very interesting new physics. What we see is that FRBs are distributed on the sky quite uniformly. There are 22 known FRBs to repeat. So at least 22 are persistent objects. They didn't blow up. And 13 FRBs are associated with distant galaxies. Now, in this picture of our current state of the art, there were also some interesting facts. As I said, FRBs repeat, so they cannot be all due to catastrophic events. And when you look at the size distributions of these repeating bursts, you see a trend which is a scale-free, but having a power law index that is very similar to what we saw about 20 years ago from magnetar bursts, with index being so consistent. On top, if you look at the waiting times between repeated events, surprisingly, of course, there is yet no physics connecting the two, the peak of waiting times distribution is around 200 seconds. That's the same as what we have seen from the magnetar bursts. So with this story, we came to the time of the pandemic. On 27 April of last year, Fermi GBM triggered with this rather strong, but not an extraordinary event. It's strong, but as I say, it lasts less than about 50 milliseconds. And that's a typical burst. But here, what I don't show, about 300 seconds after this initial trigger, there was a storm of bursts. These are all in hard X-rays, soft gamma rays. As you notice, the storm, first wave, and then the second wave are a lot more energetic than the initial spike here, initial trigger. This is what made the detector start observing. Then about 400 seconds later, there comes the main storm. And about 6 hours after this first activation, we got this big news. CHIME and STARE-2, a group in California, they observed a really, really bright, energetic radio event that had the differential measure of 333 from the direction of this magnetar, 1900 plus 1935 plus 2154. And this event was really quite high in energy, 10 to 35 ergs, nearly, making it in the league of FRBs, but of course, within our galaxy. But this is by far the most energetic event, radio event, seen in our galaxy. So this was the link that connected the magnetar burst, as you see here, as seen with Chinese HXMT, and radio events, the two peaks that you have seen right here, which are separated by about 30 milliseconds. Some FRB repeaters do emit repeated bursts like this, ranging the peak separation ranging from 17 milliseconds to 35 milliseconds. And this is a very typical behavior. And this is the X-ray burst that was simultaneously observed. It's much longer. It's still short, only about 0.2 seconds long, but much shorter than the radio. And later on, those X-ray bursts seen before and after with Fermi GBM and NICER, and the scaled FRB associated X-ray bursts were investigated, and they were shown that the burst, hard X-ray bursts that was associated with FRB was much different in X-rays as well. This is what you see in spectral parameters. The great majority do agree with one another. So not all X-ray bursts do emit the type which is associated with radio emission, fast radio bursts. So all what I've told you is that I started with magnetars being the candidates, but they are no longer the candidates. They are at least one of the sources of fast radio bursts. What makes radio bursts? It's not within the scope of this talk, but I can tell you very briefly that people invoke regular pulsar radio emission mechanism in the case of highly magnetized neutron star case and get out this coherent radiation, again, in line with how radio emission from ordinary radio pulsars come. Recently, we have been investigating some bursts from SGR 1900 plus 14 as seen with SwiftBot. And in our view, we were including the trapped fireball, which is what we expect to have when the crust breaks and charged particles are trapped within the magnetic field. Those trapped fireballs emit radiation, which are upscattered by energetic magnetospheric photons, as outlined by Yuri Lubarsky in 2002. Shotaro Yamasaki, his student, we looked at some of the magnetar bursts, and we showed that if you have an initial fireball at this temperature and process in a very simple manner, it's a toy model, so to say, the reprocessed emission by the magnetospheric particles can nicely represent the observed X-ray spectrum. So this model now has also some, hopefully, applications for the case of explaining X-ray bursts that are associated with fast radio bursts. Of course, this is how science goes. One big question is answered, but many big questions arise. For example, why not all X-ray bursts are associated with fast radio bursts? Why not giant flares emitted FRBs? Of course, these are the topics of current studies and studies that some of you might be interested. So if you want to learn more about it, please follow very recent reviews by Bing Zhang in Nature, clear understanding of almost everything, including the engines. And you will find from there many other resources. So I will stop at this point and leave some time for questions.
Thank you very much. We actually have a few questions on the chat panel. If you can see, I don't know, but I can read as well. Can you already see the questions?
Let me look.
Okay.
I can see now. Ceyhun asked, if we suppose that giant flares are formed by a magnetic reconnection in a magnetosphere, well, maybe I have no experience in case of crab type of things, but you can work out some numbers and see if it works. Sam, hi Sam. Sam Lender is asking, is there any reason to believe there is more than one kind of FRB? This is a very interesting and good question. My gut feeling is that if you wait long enough, a couple of thousands of years, I think all of them will repeat, meaning that they are most likely not catastrophic events. I'm not an expert on supernova explosions, but as far as I see in simulations, it's not easy to make a coherent mechanism to get such a beamed radiation as a result of a catastrophic explosion. So I think they are all neutron stars. Nature is not very colorful. And if we wait long enough, we will see them all bursts. But what makes them, what makes some X-ray bursts associated with or without FRB can be dependent on the magnetospheric conditions. Again, the analogy made from radio pulsar domain, you have to have a clean magnetosphere to get this coherent radio signal out, which is not the case in all X-ray bursts because we inject so much stuff into the magnetosphere in the case of X-ray bursts. So that's to be seen, but again, take my 5 cents. I think they are all repeaters. But of course, community thinks, some people think the other way, especially the rooters of the catastrophe models.
There's one more question, actually a few more.
All right. Danai, hi Danai. What percentage of FRBs associated with? Very small, one in 150, but this is what we have started. I mean, about a year ago, we have seen the first X-ray bursts. And during the X-ray bursting, we have seen the first FRB associated with an X-ray event. Let me tell you what will happen next. NICER and the new instruments, they will, of course, keep an eye on SwiftBot and GBM to observe. At the same time, CHIME, FAST, what else? VLA, they will immediately turn their attention to a bursting source. And of course, this number will increase. I wouldn't say how, but it will increase. So right now, it's just one, but it's a powerful one. It's nothing seen before. Ali Alpar is asking, repeaters and other FRBs different in any way? This is a very good point. there are some differences. It will be some radio emission properties differ to some extent as described by the first catalog of chime events. Chime, I don't know if it's already in the literature, but I have heard from someone in the chime group that they already submitted their paper, and he said about a month ago it should appear soon. So there they say that the repeater events and one-off events differ at some level, but overall they have the same general structure. The dispersion properties differ a bit.
Okay, then let me thank Ersin Hoca one more time. Thank you very much for the talk. So we can skip to the next one by Daniela Selim. She'll